So, hello, almost everyone. I wonder whether I said something wrong last time or whether people are still on holidays, swimming in the Mediterranean Sea or climbing the mountains or traveling around the world, who knows? Yeah, so thanks for coming. And we will continue today with the lecture on CMOS sensors. I just resume where I started in the lecture last time. That was 2 weeks ago. I stopped at this particular sensor derived from the Hall plate that you know, namely the vertical Hall sensor, which was obtained by considering the Hall plate a deformable structure that could be opened up so that all the peripheral contact could be aligned on the same side. And then this whole thing can be switched over into the vertical direction so that the contacts are at the surface and the deformed Hall plate reaches into the depth of the silicon chip. Yeah, this was kind of explained here where we see a cross section across the silicon chip. So you can imagine, now that's a very old drawing from a paper that first showed this sensor in 1984 by Professor Popovic. Was later, not at that time, but later professor at EPFL in Lausanne. And he was the first to describe this sensor concept of a vertical Hall sensor in this 1984 paper. And so here you see a top view. I can imagine contacts to be kind of aligned here. 5 contacts connected from different sides. And then in cross section, if you think of a cross section being drawn across here in the vertical direction, perpendicular to the plane of the projection, then you obtain this cross section and you see that, okay, there is some region that has contacts at the surface. This is the surface covered by silicon oxide with some other dielectrics. And these contacts are then the contacts of the Hall sensor. And this is then kind of bounded on the side by some P region, diffused P region. And you must imagine that this P region is also limited at the back and the front, which means that this object, this is the cross section of this object along this line. So this bounds the structure on this side, and then this is the boundary on the right side, and then you have, of course, on the other sides as well, such structures. And we have seen that you have different variants of implementing that device with equal contacts distant by equal distances. Remember that the outer contacts need to be connected because they have originated from this single contact by being cut into 2 parts. But of course, this represents one contact, which we would like to have at the same potential. Therefore, we have this connection of C1 and C5, the former only C1 connected here into this single contact. And then you see an alternative version where the contacts have been deformed slightly. They are now in a more general placement, which aims at making the resistances equal, which of course will be the case because now you only have 2 contact pairs. But still the question of how well these contacts are placed are, for instance, if I send in a current through this path, the blue path, are contacts C2 and C4 on the same equipotential line so that I can, without magnetic field, so that in a magnetic field, I will measure a deviation from 0 and not from some big offset, a geometrical offset that would be. And in order to make this even a little bit better defined, people have imagined to add another contact, some short contact in the periphery. And well, that doesn't help deeply. And will therefore mostly concentrate on this 5 contact device that I would say, has made the longest way. Now, one version that I would like to describe here is one by Ralf Steiner from ETH Zurich. That's an old thesis, but it was kind of, one of the first plate-like realizations of a Hall sensor, because you must imagine that the idea of plate is kind of gone here. Yeah, this thing may be a few tens of micrometers on a side, viewed from the top, and then the depth is 4 micrometers, the typical well depth that you have here. And so it's also like a plate, but with contacts at the top, and then the current somehow goes into the depth, and it's not a thin plate-like thing in this vertical direction. It's like many plates, one after the other, connected into a big thing, and then through each flows the same current, and you can then have this measurement at the voltage contacts, just as if you had a thin plate. Yeah, so Ralf Steiner-Vanja was given the challenge by Professor Baltes to create this real plate device in collaboration with Austria Microsystems. We have seen that name also in a former chapter 2, where we saw that where Austria Microsystems being first of all a CMOS company, and second a magnetic field sensor company, they wanted to have these vertical Hall plates, and so they said, well, we have this trench technology, so can you realize something that really looks like a plate? So if we flip this plate into the vertical direction to have it sensitive to this in-plane magnetic field instead of the usual out-of-plane magnetic field, then we would have a buried contact. So the challenge was given to Ralf, and he said, well, let's go the Popovich way, which is this figure C1, which brings the contacts all to the surface. And then he said, well, maybe there is an alternative way to reach the bottom of this plate by some, column-like contacts that reach deep down and through which current can be sent in and then can be extracted through the plate by one of the other 3 contacts. What you also see here is, in the case of the Popovich plate, some potential distribution under a current being injected. So this is a current contact 1, and the current flows in through the outer contacts along these lines into the central contact, and then you see equipotential lines that show that the sense contacts are not at the same potential. If I follow this space between lines, I end up at another location, so these must have a voltage difference between them due to a magnetic field, as indicated. And in this case, it would rather look like like what we have seen with the long Hall plate, with, however, slightly originally placed sense contacts on the surface. So Ralf said, okay, well, since Austria Microsysteme knows how to etch deep into the silicon, a few micrometers deep into the silicon, because they insulate their transistors anyway by these so-called trench isolation etches. Let's explore this feature for a sensor purpose. Again, this is using available technology for other purposes, and so he designed kind of a square-shaped trench that could be etched so that in the middle a silicon column would stand, and then he was able to use some of the implantation technology or an implantation step of the CMOS process to get some implant implanted in the surface area of this silicon, this trench. And then this is filled by polysilicon. That's all standard of CMOS technology in Micronas, in Austria Microsystems technology. And then he could realize, let's say, a contact to this outer region. And that is actually only to define a well-defined conduction channel here in the middle. So this is where the current actually flows. So the region, the access pillar for the current is through this whitish region. And then on the other side, you have then a trench that is realized by the same way, by some rectangular surrounding trench edge, which defines a nice plate-like structure that can be used for letting current flow, and that can be used for letting the Lorentz force act when there is a magnetic field available. And so with this device, Alf obtained some current-related sensitivities of 300 volt per amp per Tesla. This region of conduction was quite low doped, 8.5 times 10 to the 15. Well, that's a lower doping of a well type, and the thickness of the plate, and by this I mean the thickness of this plate, which is the thickness between the PN junctions of this N region in the middle and these P diffusions on the side of the trenches, was 2.4 micrometers. And so you have here the active region, you have here access pillar, which is also active. And so that is how this device worked. Now here is a totally different kind of device, which looks like a child's train running in circles, doesn't it? Yeah, 2 rails, but it's not that actually. It's a circular 5-contact Hall sensor. Now you might wonder why 5. You see many of those. Yes, actually, it was 64 of those contacts. But take 5, any 5 of those. Let's say, let me take a section of 5 of those. Those 5. I have a 5-contact device surrounded by another environment. Okay. But those 5 contacts allow me to drive the sensor in a way that will be sensitive to a magnetic field going towards the back of this chip. So a B, so you can imagine that there is now the plate. So a bit like this. It's not a thin plate, it's a thick plate, but it's still something 2-dimensional for the current flow. Allow the B field that goes in the back, or should I take another example so that you see that better? Let me take this guy here, with its let's say presumptive structure in 3D, and this could be sensitive to a B in this direction. So 5 contacts, allowing to do exactly what we did before with a single Hall sensor, and now you can imagine that this measurement circuitry that feeds in current and does all kinds of things, maybe 4-fold direction switching of the current. Now it's rotated step by step around this device. And when the measurement is done here, if I draw now, let's say, some Bx, so this is the X direction, here is the Y direction, and then vertical is the Z direction. So this would be a By, and this would be a Bx. So maybe let me draw this By a little bit more unambiguously. Oh, where's now my this point is too small. I need to make it larger, or maybe something like this. So let me erase this again, the Y, and say, okay, the Y actually goes kind of into the plane, and Z is out, and this is indeed, so this would be the Y direction, and this is indeed a B of the Y direction, whereas this is a B in the X direction. So when the measurement is done here, you can measure Bx, By, and when the measurement is done here, you measure less of the By and some influence of the Bx, because you are essentially measuring the B field in this direction. So when there is a By or a Bx available, you would measure a signal. And then here you are only able to measure Bx. So when you rotate, and the magnetic field is in one direction, you get some kind of a 2π periodic response, a sinusoidal or cosinusoidal response. And from the amplitude of that cosinusoidal response, you obtain the magnitude of the B field and its direction. Wherever the B field points towards, that's where the maximum of this cosinus, this harmonic function will occur. Wherever the B field is perpendicular to, or in the direction of the contacts that is perpendicular to the plate, to the local plate. And so Kajik, from a student of Professor Popovic at EPFL, demonstrated this device with 64 contacts, a lot of circuitry around, and then some bias and readout interfaces to make the interconnection possible. And he was able to resolve 14 microtesla at a cycling frequency of 13 kilohertz. So it was a high frequency operation, and the angular resolution was 0.01 degree at 100 millitesla, which is a fair technical field. So that's not a small field. A simplified version of this device was demonstrated by Mariana Banjevic, also from Professor Popovic. I was a co-examiner of her PhD thesis, so I know her work, and that's why I present it here. She said, well, do we really need 64? Can't we do with fewer? So we can even cycle faster, or why waste circuit area to contact 64 contacts when we only have smaller number? So she said, okay, the minimal thing I can do is 8 contacts in this philosophy. So we have 8 contacts viewed from the top. You see the 8 contacts arranged like this. And then you can imagine that you inject current. So here's a current source into contact 1 and 5. And then you extract it at contact 7 and 3. And if you consider this device like this, you could just imagine an imaginary cut here, and then you would have 2 5-contact devices, one in the top half and one in the bottom half. And so this device is then able to measure a B field in this direction. Again, I could write X and Y here, and a BX, not X, Y can be measured now in this biasing. Now you can do many things. You can do a rotation. So if you rotate it by 90 degrees, then you will measure Bx. If you rotate by 45 degrees, you will measure the diagonal component of the magnetic field. And but that's not all. Now you have this this top 5-contact device, and then of course the other contacts are those between which you measure the Hall voltage. So if you only had 5 contacts, that's where you would make your Hall signal. So between contact 2 and contact 8, but you have the same at the bottom. And so you in this measurement mode, those two will be connected together. And then you will measure kind of the average output of the two. And you can then invert the measurement philosophy. You can do the 4-fold switching, cyclically replacing contacts, and that leads to another biasing, as you see it here, with now the voltages measured between what was previously the current contacts, and now it's the voltage contacts, and the previous voltage contacts now being the current contacts. This is what is being done here, and this worked also fine. She was able to measure 200 microtesla of resolution and had a current-related sensitivity of 1,100 volts per ampere Tesla, and an absolute sensitivity, which doesn't mean much because it depends on the current, at this current. Yeah, and now I would like to spend some time with the linear 5-contact vertical Hall sensor, because I've been working on this device with 2 PhD students extensively in collaboration with the company Micronas, now TDK Micronas, at Hans-Bunte-Straße, and the first student was Timo Kaufmann, where you see again this idea of a vertical plate. It's not a deep thing. It's well deep, a few micrometers, 4 or 5 micrometers, and a high frequency, high voltage technology. Sorry, and then you have in this N well you have 5 N+ diffusions. These are the contacts. On top there will be metal, of course, to bring in the current or to measure the voltage. And then there are some P+ diffusions that serve to kind of separate the current flow somewhat, because it would be kind of awkward if the current flew dominantly horizontally, from contact to contact, because that's the nearest distance. The contact will prefer that, and the company said, okay, we would rather have the current flow deeper, vertically, in order for this this effect to manifest itself in a Hall voltage. And then also we would benefit of the slightly lower doping occurring in the depth of an N well. The doping of an N well decreases as you get deeper and deeper, and at some point it is so low that it is actually no longer compensating the P substrate, and that's where it transits from N to P, where you have the PN junction. There's a PN junction here, and so it is definitely better to be in the lower doped region, because the mobility, the Hall mobility is higher, so you can theoretically get better sensitivities, because for instance, the voltage related sensitivity is proportional to mu. So this is what this device was able to do in a particular design, voltage related sensitivity of 2% per Tesla, which is not too impressive when we know that we could reach 6.8 or so % per Tesla. So the geometry is not optimal. Definitely not. The input resistance is 2,200 ohm. And then, well, at this kind of high input current, which would correspond, I think, to 11 volts, which is a lot. Certainly not the voltage at which this device is operated in Micronas chips. Well, at this unrealistically high current, you have also a super large offset, 15 millivolt. Imagine that the signals may be in the area of tens of microvolt, and now you have 15 millivolt, factor 100 or 1,000 more than useful signal. So the compensation is tricky, and you need to do compensation, and yet you are resolved in the resolution. And so that was kind of the starting principle, or the starting challenge of Timo Kaufmann, to make these sensors better, to understand why they are so bad. And Timo, after some design and production phase at Micronas, turned up with some measurement, which I can show here. So, of course, you know how the 4 contacts, the 5 contacts are connected. So the outer ones are connected into a single contact, and then this is kind of the partner of the middle contact, and then the 2 halfway contacts are the other pair of contacts. And now you can do 4 measurement modes corresponding to the current rotation by the cyclic permutation of contacts. And Timo called them mode 1, 2, with opposite direction. That would be a 180-degree rotation of the contacts. And then the other is mode 3 and 4, where what was input contacts, where the current flows, becomes now the voltage contacts, the voltage measurement contacts, and vice versa. What was previously voltage measuring contacts now becomes the current injection or extraction contacts. So these are the four modes. They're not numbered as naturally in the cyclic permutation. It's kind of this and that. So I'm indicating the current direction in a normal plate would have mode 1, and then not mode 2, but mode 2, and then mode 3, and mode 4. So this is just shuffling around the four modes, but they are all there. And then I remember in one of our seminars in my group, he presented his results and he said, yeah, I find the following result. You know, I have this in modes 1 and 2, I have this offset, as I just said, in the order of 10 millivolts. For 2 of the modes, they are kind of linear, and for 2 other modes, they're totally nonlinear. But if I average them, as I should do in current rotation, they almost eliminate. They almost cancel. They cancel. I mean, you can't even see that they don't cancel, but they don't cancel completely. And what remains uncancelled is still pretty large. We're talking about millivolts here. So even if it's a tenth of a millivolt, 100 microvolts, still a large offset. And so he said, well, so that's what I find. I don't understand what's happening. And worst of all, for every sensor, it looks different. But I always get this pair and this other pair, and I can't make sense out of it. Nothing systematic. I said, hey, this is very systematic. We just don't understand it. The data are whispering some kind of truth into our ears, but we can't make sense yet because we don't speak their language. So what do they tell us? And I, after some thinking and analysis, I thought, okay, so here we have something. Maybe this is some lower, or some smaller effect, and actually we should consider those 2 responses as equal and linear. Now, if I draw a line between the other contacts, between the other modes, between the red modes, I get some line in between, and then that has amazingly just the opposite slope of the modes 1 and 2. And then on top of that, for some unknown reason, they split with this parabolic addition, which is added on top of the linear curve. And if that is the case, of course, if the blackish above and the blackish lines below have equal but opposite slope, they will cancel, and the parabolic contribution, one's positive and one's negative, will also cancel. And then the average of all is going to be 0. So that was just a geometrical observation, and it seemed to be the case for all the different seemingly unsystematic measurement results that Timo obtained. So we had to understand, and I said, okay, let's consider this device a little bit on a more fundamental level. So I drew this equivalent circuit. You have this interesting linear arrangement of contacts. And I'm biasing your minds now by saying linear, in order to divert you from any other idea. Now you can only think linear, and then there will be boom, big surprise. Okay, so of course, I mean, I can say, okay, between these contacts we have some resistance, so some RO, O for outer. This is the outer contact pair. So on this side, the same, R outer between contact 4 and 5, 4 and 5. And then between the inner pairs, 2 and 3, and 3 and 4, we have inner resistances. They might be maybe slightly different, because here, I mean, if we send in a current from 2 to 3 to measure the resistance, it can develop in a certain way. But here, because of this boundary of the N well, probably the resistance is going to be different. Not exactly equal, because the current flow might feel this lateral end of the structure. Okay, so that's why I defined these two different kinds of resistances. And then we have this connection on top, which has some resistance RS half. That's how I call it. And then actually we have 4 contacts, C0, and then C2, 3, and 4. Yeah, and what was 1 and 5 is now connected into what we call C0. Okay, so this is our linear device. And I said, okay, now that I have a schematic, I can twist it around and I can do whatever I do. So here's an equivalent arrangement of exactly the same information. You have these 4 contacts, C0, 2, 3, 4. You have all the resistors in between, and then some additional things. So for instance, between contact 2 and 3, we have resistor Ri times 1. So please disregard the other little writing here in the bracket. We have Ri between contact C2 and 3, like here, Ri. The same between contact 3 and 4, Ri times 1. And then between contact 4 and 5, we have R outer times 1. And between 2 and 1, we have also R outer. And then we have RS half on both sides of contact C0 connecting to C1 and C5 respectively. So this is equivalent to this arrangement. Now, when you look at that, what do you call it? A Wheatstone bridge. Yeah, and it's a hard thing to look for ages at that structure and say we turned a plate into something linear, and then at the end to say, hey, this is still a Wheatstone bridge-like structure. It took the PhD student did not see it, and I only saw it once I drew the schematic, because then I was more flexible in my mind. And then suddenly I said, oh, this is a Wheatstone bridge. I can do an analysis. And this analysis can incorporate imperfections. For instance, these outer resistances may deviate from each other slightly. They may not be the nominal resistance RO that they should have, but they can be, let's say, modified by 1% plus minus, because of doping inhomogeneities or shifts of the contacts. It's possible. So all these resistances have some little shift, some stochastic, some arbitrary, statistical shifts added to them, principle. And so do these connections up there. These are metal lines. RS is rather small in comparison with RO and RI. And there might be some asymmetry also there. One might be larger than the other. So let's take this into account. And then there comes another thing. These additional things. Let's say that the resistance between contact 2 and 3, R2, 3, not only depends on some value that may not be perfect, but it also depends on the voltages applied to it. So why the hell should that be the case? Well, between contact 2 and 3, where is 2 and 3? Here, we have a PN junction. And the width of that PN junction depends on the applied voltages at the contacts 2 and 3 with respect to the P substrate. So the resistance depends on the voltages that are applied. And to first order, we can model that resistance change because of the applied potentials as a linear function that implements V2 and V3, like this, the average of those voltages. It's the average voltage from the left to the right between the contacts. That's a reasonable assumption. And I do so for all the 4 contacts or contact pairs that are relevant here. And now, of course, we have the next problem, because the Wheatstone bridge has resistors that depend on the voltages within the Wheatstone bridge. So usually you have the resistances and then you just calculate your half bridges, your R divided by R1 plus R2 and blah, blah, and then you have the voltages. And now the voltages depend on the driving condition because yeah, it's an intricate problem. But fortunately, you can disentangle this problem by doing some Taylor series expansion, small. I mean, these effects are small, and so you can do a Taylor expansion, and that ultimately enabled us to model that device realistically. And the outcome is shown here. So for small resistive, for the following values of the parameters that appear there, yeah, we obtain a pretty decent fit of what we observe. So that was black curves, now they're blue. Yeah, the red curves are still red, and then here's the average of the red curves, which goes down here. Yeah, and the blue curves and the red curves are the ones that were measured. And so with resistances Ri and Ro, yeah, with these values, and then Rs much smaller because it's metal, 22 ohms, and then some little asymmetry of the resistances of 1 part per thousand, so 0.1% in inequality of resistances, and then a little bit of differences between these beta coefficients. What were those? The beta coefficients are the ones that describe this junction field effect. So these junction field effect coefficients are assumed to have 10% per volt and 9.7% per volt. So roughly 10% for both inner and outer resistors. And with that, you're able to model the measurement rather decently. The through curves are the model curves, the dots are the measurements, and I think we have caught the essence of what the measurement says. And it shows actually that if the betas are zero, if there is no junction field effect, then those parabolic responses are gone. The response will be like the black curve, black instead of red. And the black will be just opposite to the blue. And then they will cancel. And when you switch on and the position of the blue and the black curve, the slope of the blue and black curve depends only on, well, essentially on these asymmetries. How well the resistors are matched. Resistor mismatch always causes some offset in Wheatstone bridges. And if this is a random parameter, then the offset should be randomly distributed. That means that the blue curve should be randomly distributed to positive and negative values around some zero, for instance. And then if there is a BI and BO that is systematic, then it means that the split of the black curve into the red curve should be systematically the same in all devices. And that's exactly what Timo observed. He saw that the blue curve and the blackish result were distributed randomly, always opposite to each other, but the parabolic split was always the same. And so I said, in that meeting, come on, I mean, we need to find out. And so we found out what the causes were. The causes are described here. This has a minor effect here. And so in one of the papers, or actually here also in his thesis, Timo observed that A1 and A2, the linear response for modes 1 and 2, and the linear response for modes 3 and 4 are indeed opposite. And if you just take the average of those and plot it as a function of the samples for many samples, he measured that for a whole wafer, and then he found that this is statistically distributed around zero with a standard deviation. You see the standard deviation here of 0.79 millivolt per volt, and centered rather close to zero. Yeah, slight offset was also observed. Yeah, so you can ask, is this significant, or is it due to the fact that he only has a finite number of measurements? And then the B coefficients could also be measured, and then he found that B3 and B4 are opposite to each other. And of course, B1 and B2 is basically zero. That's also a result. And then he found that the mean is indeed different, significantly different from zero, and the different values scatter around that mean very closely. Yeah? So with this, we could think about the real cause of the imperfection of the sensor, because given these large offsets and these effects, it was not amazing that the average of all the curves, namely this well, 3 to 4, average of modes 1 to 4. Yeah. So this curve, it was not amazing to see that this curve was not sufficiently close to zero to make a high resolution magnetic field sensor. Still a beautifully linear sensor, but not a high resolution for small magnetic field sensor. And so what was the reason? Well, it is the reason is that this Wheatstone bridge, although with respect to left and right, it is quite symmetric. But with respect to this axis here, it is not symmetric. So it is slightly less symmetric than a standard Hall plate, which is the symmetry. We always do these Hall plates in a symmetric way. And that has not only an aesthetic purpose, it makes the sensor better. And here we can't do that because the structure is like that. It has this built-in asymmetry, or still symmetric, but not as symmetric as we would like to have it. And so the next step was to say, okay, then we need to make it more symmetric. And I apologize, I don't have the slides here, but I will show you some results from a paper. No, not this one. Where is the chapter 3 publication? Yeah. So with Timo, actually with his successor, we wrote this this paper based on, I would say, the final phase of Timo's PhD thesis, when suddenly our understanding turned into a better structure. We call this the fully symmetric, it says symmetrized vertical Hall sensor. And actually, so this 5-compact device, how can you symmetrize it to make it more similar to a Hall plate with its full 4-fold symmetry? That was the idea. And we had written a patent that Micronas is now using as the basis for the production of their sensors. So the vertical sensors of Micronas are based on this patent, and they're producing hundreds of millions of those. So what is the idea? I can show that here. So here you have the normal Hall plate with its 4 modes. Now you're totally blasé, you know everything about that. 4-fold rotation, contact switching. Here you have this vertical Hall plate with its inherent asymmetry, because it's not as symmetric. So how do you make this more symmetric? Well, I say, okay, let's cut that device into 4. Actually, I make 4 cuts. Then I have contact 1, 2, 3, 4. Let's say C1 is here. Or C1 is still here on the left. 2, 3, 4. And then I can discard this outer thing. Now I have 4 wells with only 1 contact. Now what I can do is I can connect these wells by some side contacts. And then here, from here to, there is nothing. Okay, so I need to go to the beginning. Now I have 4 separate structures that cause 4 contacts to be connected to a conductive semiconductor region, which now is not as simple as before, but every single one of those elements is identical to the other, apart from the usual small geometrical and doping related imperfections. So if I imagine these black lines to have 0 resistance, then this device is electrically symmetric because it consists of identical elements. It doesn't have this outer boundary that makes it special. This is not more special here than this, or this, or this. There is no outer boundary. You can also imagine to just switch the order of those. Electrically, it's still the same. So what was inner becomes outer. So this is a symmetrized version. And so based on this element and its analysis and all the things that we could do, we proved that actually, is there some table? So we proved that we can do a device with much lower offset. So let's see, there must be a table somewhere. Yeah, so table. The 5 contact and the fully symmetric device. You can compare here. Someone read these numbers, or should I? No, you cannot. Thank you for being so frank. Yeah. So now, still, is it okay now? Barely. What about Matthias? It's better. Okay. Yeah. So operating conditions. So what do we have? Well, different input resistances. Sure, not amazing. The offset voltages of the individual phases are similar, but the residual offset is much smaller. It's decreased by a factor of 10, which means that you can do 10 times better. You can measure 10 times smaller magnetic fields. And then there was another version which has this, I would say, mythical name, Ulof's ultra low offset vertical Hall sensor. Whereas the FS-VHS was the fully symmetrical vertical Hall sensor. Whereas this was the 5 contact vertical Hall sensor. So the Ulof's, what is that? That is a connection of 4 such devices into one big device. So here you have the vertical Hall sensor viewed from the top, and then a second one, third one, fourth one. And now the first element is connected to the second, to the third, to the fourth, and vice versa. And that is a parallel operation of 4 devices in the 4 current directions, or the first 4 cyclic permutations that you can operate. So instead of doing the operation in the cyclic permutation in fully symmetric vertical Hall sensor 1, I have it also implemented here immediately, and here immediately, and here immediately in phase 2 and 3 and 4. And of course, I have 4 output contacts. So I can operate this device like a parallel operation of the device in 4 operation modes. And then I can still do the switching. So maybe this helps, and it seems to help, at least in the table. Where's the table? We see that the residual offset is decreased yet by a factor of 10. So by just some design implementation, based on understanding of what the drawbacks are, we could improve the sensor by a factor of 100 with respect to its offset. That was quite remarkable, and I was very happy about that, because it showed that the systematic analysis of observations is an important aspect of the scientist's life. And it is worth it. It's not just, oh, let's try out something and then you fiddle something. But the data say something. What do they say? What can we conclude? And then we can really improve the sensors. So here is the residual B that can be resolved. And so there was 2 millitesla for the 5 contact vertical sensor, was 140 microtesla for the fully symmetrical, that was 40 microtesla for the Ulofs. So this is a paper published by Christian Sander, who really worked out the details, the physics of these fully symmetric vertical Hall sensors, and then related devices like 2D devices and others in this paper and other papers of sensors and actuators. So I go back to the lecture material that you have and would now like to discuss a few alternative concepts that are also interesting, that have been around and that are worth discussing. So some concern the split current concept, others the field effect devices, and then some magnetotransistors, and at the end I have some resonant devices. So those are then not transport based. They have other mechanisms implemented. So what is the split current Hall plate? Imagine that you have this conductive plate viewed from the top with contacts on one side and on the other side only. And those on the top side here are split into 2. So don't imagine this to be a vertical Hall sensor. It's a plate in the plane of the chip. The chip plane is the same as the projection plane here. And so what will you observe? If you apply a circuitry that injects a current I into this common contact and somehow ensures that the voltage here and here are the same, then it is likely that under a magnetic field, and I should maybe draw this magnetic field B, there will be an oblique current flow. So for instance, oblique in this direction, and that means that more current likely flows through this contact into the device than through that contact. So if you measure if you have this measurement instrument to measure the current that flows through those 2 branches, you will notice a difference. One will be I half plus some increment, and the other one will be I half minus the same increment. And that difference, if you are able to measure that difference, so this delta I, which actually is called IL, then this IL is very likely, no, it's evidently proportional to B, to the B being applied. So that's an interesting idea. And so you can ask, is that better? No. And so if you do an analysis, you can calculate the current difference based on some geometrical considerations. And then you will say, okay, so there's the current density times the length of the contact times the thickness, and then some tangent hyperbolicus. And yeah, so what is IL? No, L is this length here. And actually, this here is the width. Is that so? No, it's wrong. This is the length, and this is the width. And so the relative currents difference can also be calculated, and it's going to be with tangent of theta Hall. It's going to be approximately mu h times b times some geometry factor. And that's now the Hall current difference per input current. It's similar to what we used, what we called the voltage related sensitivity. This was output voltage per input voltage per B. Here it's output current per input current per B, or actually input current at B. And if we then also divide by B, then this is going to be gone. So this would be a sensitivity, and it has the same units as the sensitivity of SV. So it's kind of like SV up to now, or earlier. I should call it earlier. But this is a current device. We don't measure voltages, and but if you measure current per current, then you have an absolutely analogous result, which shows you that this device is not better than a voltage-operated Hall plate. Such devices have also been implemented as field effect transistors. So on the left, you have a traditional field effect transistor with a source and drain, with a gate plate over an oxide, an insulator, over a channel that can then be conducting under a suitable gate voltage VG. And so we'll have a source drain voltage flowing. But if you also have lateral contacts, and if this device is pervaded by a magnetic field B in this vertical direction, then those lateral source drain contacts, which will now be called sense contacts 1 and 2, will feel a voltage difference, just if it was a plate, a majority carrier plate. And so this is the traditional translation of a Hall plate, a normal Hall plate, into a so-called MACFET, a magnetically sensitive field effect transistor. And the Hall voltage measured between those two side contacts is then some geometry factor multiplied by the source drain current, multiplied by B, multiplied by what we usually call the Hall coefficient RH, which is some Hall scattering factor, some scattering factor divided by usually Q and T. So that's what I say here. So RH is usually minus Rn divided by Q and T, and those symbols are now replaced by Rn channel and by Q channel, where Q is the 2D density of charge carriers in the channel. It's the numbers of carriers. It's not the numbers of, it's Q times the number of carriers per square centimeter. So it's the channel integrated over the depth that gives you a number of carriers, and those have charge Q, and this is this channel charge density, as it is usually called. And Rn is replaced by Rn channel because it represents scattering. I said that its value depends on whether impurity scattering dominates or lattice scattering dominates. And here we have another scattering mechanism, namely the scattering by the surface, by the oxide interface of the field effect dielectric with the channel. So those will also hinder, and therefore the scattering factor is going to be different. And so will the Hall mobility, because the Hall mobility is some mobility times Rn channel here, and the mobility of the charge carriers in the channel is also different from it is usually, because they scatter on the surface. So there is this thermodynamic factor, there is this conductivity parameter mu, and usually it is smaller than mu h, the normal majority carrier mu h. Yeah? So it's not such a great idea to do this these field effect transistor based magnetic sensors, because they are worse than just diffusion based devices. Yeah? But yet, you know, in research, obstacles don't disturb people. Yeah? They say, okay, let's try and see whether this assumption is correct. Yeah, it might be, you know, there might be this miracle, and then we would be famous, and then people try out things, and then later they're smarter because they understand why actually something is not better. They think about, you know, how this should be written and so on, and then of course also the dual drain magnetic field effect transistor has been invented with a split drain, common source, and then current is injected in either direction from left to right or from right to left, and the current is measured in these two drain contacts under a magnetic field. And again, don't expect anything sensational. Yeah, this is the basic formula, and this mu h is simply going to be replaced by mu h channel. Yeah, and then that's it. Or also it has been tried in with transistor-like structures. So these are magneto transistors. So it is easiest to observe in this vertical device that is fundamentally based on a bipolar transistor. So a bipolar transistor has usually an emitter, like here, and then a base, which is given by this whitish area, and then a collector, which is coming in usually only from one side towards this base and emitter pair. And then there is a contact by some buried, highly doped arsenic or antimony doped zone, which is connected to the contact out there. So we have emitter base collector. And then there was this period when people did these symmetrical dual collector vertical magnetotransistors, because they said, okay, we can have a second E base collector device here, and transistors are known to amplify. Bipolar transistors are amplifiers also under certain operation modes. So maybe we can obtain these super duper high sensitivity devices. Yeah, and it turned out to be not to be the case. Yeah. So what was the idea behind? When you have a magnetic field now perpendicular to the structure, therefore lying in the plane of the chip, yeah, it will kind of direct the charge carriers from one side more to the other. Yeah, and so it looks a bit like a split drain current device. Yeah. So the question was, is that really the fact? Is that really what makes this device sensitive? Other people have said, no, that's not the case. It is some modulation of the emitter collector base, depletion zone. That's where the thing is developing. And well, whatever the conclusion is, actually the sensitivity is quite low. Yeah, it's quite low. Actually, it's normally low, with a few percent per Tesla at best. So this is not something extraordinary. It's a delta I per IC per B. So this is meant to be, of course, both below the bracket, the division sign, and so you have absolute decent but not extraordinarily high sensitivities. And if you implement this device in a horizontal structure, with an emitter and then some base and then some collector structure, of course, this is going to be a very crappy transistor, because you have this large base distance, which totally contradicts the requirements on the transistor. The base usually is very thin. The thinner, the better the transistor as an amplifier. Here, not so much is happening, and so this was a crappy device, and therefore it is sufficient to say low sensitivity. Don't try anymore. Yeah? But people try it, yeah? And then they're smarter. Okay. Now, in the last few slides of this chapter, let me talk about some totally different magnetic sensors, just for the fun of it. Yeah. So these are not CMOS based, but it's, well, one is CMOS based actually, but two are not. Yeah? So what is this third example, inspired from, is what the first two examples say. Of course, you all know that a compass needle will align in the direction of the magnetic field. Yeah? Now, usually the compass needles are in a space filled with some liquid, some oil or so, yeah, so that the needle is dragged into the direction of the north. If there was no oil, if the needle was totally well suspended, what would it do? It would be dragged towards the north, go too far, and then go back, or oscillate, yeah, around that middle position, yeah. And you would have to look, where's the middle? Oh, that is going to be north. Yeah? Not such a practical method, because we're not good in averaging. Exactly. If we have something still, we can direct, that tree is north. That's where I have to walk. Yeah? And so you can imagine that such a needle, a dipole, magnetic dipole, is hinged on a spring. And this spring can be put into resonance. Yeah. So now the measurement principle is totally different. We're not measuring the oscillation around B, but we have this resonance system. Yeah. The needle has its own frequency of what is it? 238 hertz. Yeah. So you can probably hear it. Yeah. If you go close, if it wasn't a dipolar acoustic wave that was emitted, that dies off very rapidly. But it is clear that if you orient the system with the magnetic needle towards B, in addition to the mechanical spring, it also has a magnetic spring that tries to orient it. If you have it under 180 degrees, then actually the pole wants to, the wrong pole wants to be driven away from the north direction. So in one direction, the resonance frequency is increased, and in the 180 degree direction, the resonance frequency is decreased. And so you can rotate the device, and then you can measure the resonance frequency, and where the resonance frequency is maximum, you know the north is there. So that is the principle of this device. By trying to pronounce it, Leichle or Leichle, derived from some French maybe, operated at 238 hertz, with a sensitivity of 31 kilohertz per Tesla, okay, and a resolution slightly below 30 microtesla. That's what the paper says. So that's okay. It's okay. It's the fact. The question is how to implement this device. How bulky will it be? How sensitive will the mechanical spring be? You bang it and boom, the spring is gone. Maybe. Semiconductor device is robust. So always have to consider this. But the resolution was decent. Here is another device by Bareni that is also quite original in its construction. So you imagine this mass here, this suspended mass hung on those two springs. You can let it resonate in this vertical direction. If there is a fixed suspension, boom, it will be a mechanical resonator going up and down with some spring constant divided by K, square root thereof in resonance, angular resonance frequency. Now, those springs are not suspended on a fixed structure, but on something else deformable that is able to carry a current. And so imagine that the magnetic field points into the plane, into the projection plane, or comes out of it, and you send currents through these two lateral suspensions. Of course, the current that flows here along feels that magnetic field. And by the Lorentz force, it wants to, the carriers want to go in one direction, perpendicular to both their velocity and the magnetic field, that is outward, for instance, or inward, depending on the direction of the magnetic field. That is, this suspension here is pulled apart or compressed. It's like a violin string, that you turn your violin. I don't know how this part of the violin is called, this knob, where you stretch the spring more or less to adjust the tune. Well, that's the same effect that is happening here. And that detuning of the resonance frequency will be a function of B. And if it is in linear response, it will be proportional to B. So that's what Bareni described. The natural resonance frequency of this resonator is 27 kilohertz. No, much higher, less immune to other frequencies that surround us. It's beyond the acoustic frequencies to which we are sensitive. And then it is said to have a sensitivity of 88 hertz per Tesla, which is not too impressive. But yet he says that he's able to resolve 37 microtesla. So it must be that the resonator is a very high Q resonator, which is also amazing because the structure is dynamically not so well balanced. So I have my doubts, but anyway, that's what the publication says. And then there is this third example on the right by Robert Sunier. That's a name from the French-speaking part of Switzerland. And he also worked at ETH Zurich in the group of Professor Baltes. And he conceived a CMOS-compatible magnetic resonant sensor, where you can imagine a cantilever that can vibrate out of the plane. So this is the cross section. The line that you see here is basically the plane of the chip. And this resonator can resonate out and into the plane of the chip. And viewed from the top, you have this cantilever beam, this rectangle being supported strictly here, clamped on this side, and then free to resonate at its free end, up and down. So there is a deflection of this thing, out by some axis Z, and then there might be some maximum resonance amplitude delta Z. But let's call Z the deflection of this end of the cantilever. Bad drawing. I have to do that again. So I don't need this. So let's assume that the cantilever is now deflected, by how much? By Z, okay? And Robert Sunier lets his cantilever resonate at 175 kilohertz. That's given by the dimension and the stiffness of the material, silicon oxides and nitrides, the various layers of the CMOS, the dielectric layers of the CMOS process. And the sensitivity, he claims, is 60 kilohertz per Tesla, and the resolution he enables with his device is smaller than 1 microtesla, which is quite remarkable. And how does he achieve that? Well, he says, okay, I use the Lorentz force also. And I send a current along a conducting line that encircles the periphery of that cantilever. So we have this magnetic field. So the magnetic field, let me draw it in yellow here. The magnetic field goes in this direction. This is B. So the magnetic field goes in this direction, B. And when you imagine now a current going in this direction, there will be a force acting on the carriers that flow along this segment of the line, the Lorentz force. And the force is perpendicular to the current direction, or current direction, the velocity of the carriers times minus q, the electrons cross B. And that is a force that points out of the plane or into the plane, into the chip or out of the chip. So imagine that you can, you could now do a measurement. First idea that would come to mind is to let the current flow back and forth. And when you do that at the right frequency, at the natural resonant frequency of the device, it will be excited up and down, up and down, up and down, and therefore will get into resonance. So you can measure that, the frequency at which this occurs. Okay, that's the natural frequency, but you can also measure the amplitude. And of course, if there is no B, then there will be no amplitude because there is no Lorentz force. So the amplitude might be proportional to B. But Robert Sunier said, no, that's not what I want to do. I don't want to make an amplitude measurement. I want to make a resonance frequency measurement. I need to modulate my resonance frequency in a way that is proportional to B. So how shall I do that? And he implemented that in his system by having the current proportional to the deflection. So when the beam is deflected upward, the current is positive. When the beam is deflected downward, the current is negative. So there is a feedback loop that measures the position of the beam, and that then determines how much the current needs to be. So it's an electrically more complicated system. Here you have a perspective view, the clamped edge of this cantilever, composed of the dielectric layer sandwich, these 4 or 5 micrometers from the field oxide up to the passivation. And then embedded within is very likely, well, he calls it a coil. Of course, a current loop can always be called a coil. And this is made from aluminum, to let as much current flow through with as little voltage as possible. And actually, he not only implemented one coil, but a whole loop, three times or 4 times around this structure to boost the current, to boost the Lorentz force. And how is this produced? Well, you have your CMOS technology, you have some NP N structure in a P substrate. You can do an electrochemical etch stop, and then you can do a deep reactive ion etching from the top, and that releases your structure, and then you have your coil. And actually, to be precise, he had not only 4 coils, but 8, because there is metal 1, metal 2. So he exploited all the metals to make the Lorentz force as large as possible. So this, what you see here, is basically a cross section along this direction. And the cantilever doesn't look like only a cantilever. This is the cantilever, but then it needs these currents on the side as much as possible to get as much Lorentz force as possible. So this is also optimized to produce as much force as possible in comparison with the stiffness of the device. And then there are some sensing elements here, piezoresistive elements that allow to measure the deflection of the bridge, and whose signal is then fed into a circuitry that says how much current must flow. Yeah, and that's this, and the structure is, as I said, realized by some reactive ion etching and silicon etching from the back and from the front. And so the mechanical model of this structure is that the structure wants to work against its own deflection by a mechanical spring constant. It wants to be in the middle. Any deflection is bad, and so the middle is best. That's described by this term. So that's the mechanical spring. Then in a dynamical system, of course, there is this mass times acceleration term. Now, the second derivative of z with respect to t. So that's the classical ingredient of a harmonic oscillator. And then this harmonic oscillator is driven by a force. That's the third term that you need. And this force is now, by design of the system, proportional to a current and B with some effective LC. And then this I is now by the system defined to be proportional to Z. So the measurement of the deflections through those sensing bridge resistors enables to set I proportional to the out of plane deflection. And so that's what is the driving force now. And the driving force now depends on Z. So you can rearrange the equation into a homogeneous differential equation without a driving force, but with a spring constant that incorporates this K minus this other ingredient, which is kind of a second spring constant, which can be positive or negative depending on the value of B. So this is here meant by K total, which is this guy minus this guy. It depends on B. It is divided by M. You take the square root. You divide by 1 over 2 pi. That must be added to obtain the resonance frequency in hertz. And so this K total is K minus BLC KB. KB is just some system constant that translates the output here, the input deflection into a current that flows. I don't know, some little knob value that can maybe be set by some appropriate switches. Yeah, so now that you have this, the resonance frequency is a function of B. And it depends as the square root of K minus BLC KB. And if this is not too large, then this can probably be expanded into, again, a Taylor series, into the fundamental resonance frequency minus a change that is proportional to B. And that is then the sensitivity, the 60 kilohertz per Tesla. Okay, that sensitivity, that linear response of the resonance frequency divided by B makes then the hertz per Tesla. So that is quite intricate, and it is a system realized in CMOS technology. Now, I think I will shift because we're approaching 5:30. I would say that the last example of a resonance structure I will shift to tomorrow, and then we'll leave it there. Okay, I have now to stop. Where do I stop? Here. Stop recording.